There's a lot of confusion about what a measurement is in quantum mechanics, but there's a way of thinking about it that clears up much of the confusion. Let's start. Here we have a die with 6 faces. What value does it have? Let's find out. Well, it has a value of 5. What we just did was to measure the face property, F. The flat surface is our detector, and the die is the target that is being measured. And here's the key thing. The detector interacted with the die and forced it to commit to one of the 6 values. Let's say we want to measure something other than the faces, like the corners. Here each corner has a number. To measure the corner property, we cannot use the flat detector from before, so instead we use a different type of detector. It interacts differently, and the die now has to choose a corner instead of a face. In this particular case, we measure a value of 4. So the take-home message is that a measurement is an interaction. The target interacts with the detector. Let's put that on a plaque. A measurement is an interaction between a detector and a target. Let's look at the mathematical notation. The phase detector is modeled with an operator, f hat, which gives us 6 eigenstates. An eigenstate is whatever the detector can measure. In this case, we got the eigenstate f2. The corner detector has a different set of eigenstates because it can only measure corners. Now, when the die is still in the air, we don't know how it's going to land, and we say that the state is in a superposition of eigenstates. When the die is measured, it is forced into an eigenstate of the detector. We say that the state collapses to an eigenstate. For the corner detector, we write the state as a sum over the other set of eigenstates. And again we collapse to one of those eigenstates. Now let's see what happens if we measure twice in a row. Here we have 4 dice, all measured to have the same face value. We can again measure the face value, or we can measure the corner value. In the first case, we get the same value because there is no superposition. We already have an eigenstate. But in the second case, we do get different values. This is because the F1 eigenstates is really a superposition of corner eigenstates. So when we look at this die, is it in a superposition or not? What's your answer? Well, we cannot answer the question unless we also specify which eigenstates we have in mind. That is, which detector do we have in mind? With respect to a phase detector and the phase eigenstates, there is no superposition. But with respect to a corner detector, we do have a superposition. This point is also worthy of a plaque. A superposition is always with respect to some detector. You can't just say this particle or this cat is in a superposition without specifying what it is that you want to measure. So we just saw that when a die is in an eigenstate of the detector, there is no uncertainty. But when they're not in an eigenstate, then we do have uncertainty. We can also illustrate this uncertainty with consecutive measurements. We prepare the system to be in the phase state f equals 5. This value is certain, which means that if we again measure the phase value, we again get f equals 5. But the corner value is uncertain. This time we happen to measure c equals 7. When we measure it again, we again get c equals 7. But now the phase value is uncertain. If we measure it again, we may not get the original value. Indeed, this time we get f equals 3. We say that faces and corners are incompatible observables. This means that measuring one messes up the other. So our third and final plaque is about the uncertainty principle. For a die, we cannot know both a face value and a corner value exactly. And there are many ways of saying this. Since we focus on detectors, we can say that a target interacts destructively with incompatible detectors. And that's it for this video. In the next video, we look at the so-called measurement problem and how much of a problem it really is. I'll see you there. For more videos, go to physicsisnotweird.com. And I'm Eyvind Bernander.